Okay, hello everyone. Find both the scalar projection and vector projection of B onto A. Okay, so we're just going to have to interpret what these words mean. And also notice that they put B and A in these sort of angle brackets. And it really doesn't matter. They put little arrows over them. We could have written A equals -2, 3, 1. Right? It's the same information. It's just, you'll see this in different classes written in many different ways. And part of this class is to just recognize they're all the same thing. And so first, a picture. Picture. Period. So B and A are just two vectors, and so I'm just going to draw a cartoon. Here's B, and maybe here's A. Okay? Now, what's the vector projection of B onto A? I'm going to imagine that the vector projection is this vector here. In other words, it's a vector. So that this is a 90-degree angle. And so I think that V, I'll label it V. I'm just going to give it a name. I think V is vector projection. Now, what's the scalar projection? I think the scalar projection is just the length of V. Length of V. So that's what I think the scalar project. Scalar is like a number, like 2 is a scalar. And it scales vectors, so I'm just going to say a scalar is a real number. Okay, and so yeah, it's very similar to the last problem. It's just that we're only looking at this piece of the picture, and we don't have a plane, and we don't have a surface that the plane is tangent to the surface. We don't have any of that. So it's actually a little easier. Okay, so let's compute. V is equal to, well, some amount of A, right? V should be in the same direction as A, so we have to shrink A down until it's exactly at length of V. And so the length of V is determined by B, so that's why we shrink it by B dot A over A dot A. That's it. That's the answer. So let's compute. What's B dot A? -2, 3, and 2. Okay, what's A dot A? 4, 9, and 1. Times A. Okay, so this is 3 over 14. Times A, well, A is -2, 3, 1. And that's it. That's our answer. This is the vector projection. Okay. Now, okay, what's the scalar projection? Well, it's just the length of this vector V. So the length of V is equal to, well, remember, it's the square root of V dot V, which is equal to the square root of the sum of squares of the components of V, etc., etc. And so, okay, we can do this. Let's see, square root of, now something. What's the components of V? Well, I have to bring this 3/14 inside. So the first component is -6/14. Okay, so -6/14 squared. Plus, what's the second component squared? Well, it's a 3 and then a 3/14. 9/14 squared. Plus, okay, what's the third component? Well, it's a 1 times a 3/14. Okay. And I add those all up, and then I take the square root. This is, you can think of as Pythagorean theorem. And this is some number. This is a real number. And and it is what we call the length of V. And, okay, I mean, do I want to compute this? I don't really want to do it. But, okay, let's just see how you would. So 14 squared is going to be in the denominator of all these. And then I'm going to have a 36 and an 81 and a 9. Okay, these together are 90. That's helpful. And then these together are 126. Okay, so the square root of 126 divided by 14. I took the 14 squared and I applied the square root to it. And okay, so this is some number. It's still not super helpful. It's a square root. Of course, whenever you take the length of a vector, you have to take the square root. And so it's up to you whether you want to keep it here or here. Okay, but let me label. This is the scalar projection. And it's just the length of the vector projection. And honestly, both these things are very related, and you'll use one or the other in a problem.